Hi, my name is Christopher Schulte, and today I'll be talking about lab number 1, which topic is constant velocity. The purpose of the lab is to observe the motion of some object that is moving at the same speed without changing direction. This was to be carried out by recording the motion and creating a computational model, then comparing the predicted versus actual graphs. Utilizing physics principles, the goal is to report the observations on both objects' motion and the developed computational model. Then we're to discuss the differences between the model and the observations made. The fundamental physics principles and models that were used included constant velocity, which states that when net force equals 0, the object will maintain the same speed and direction, or the velocity, until acted upon by another force. This is reinforced by Newton's first law, which states that an object at rest will remain at rest, and an object in motion stays in motion with the same speed and direction unless acted upon by an unbalanced force. Also, we utilize Newton's second law, which relates the net interaction between the system and surroundings to the observed motion, or changes in momentum of the system. The system used in this experiment was the red cart. Similarly, its surroundings were gravity, the normal force exerted by the frictionless track, the push force before the video started, and as well as some slight friction. The results of the lab, as predicted, the red cart moved at a near constant velocity across the track because no net force was acting on the cart for the duration of the video segment. However, there was a slight variation in the actual versus predicted distance traveled, likely due to the minimal presence of an unbalanced external force such as friction. Data and analysis. Here's the tracker data that we got from taking a video of the cart in motion. As you can see, the cart moved from the right to the left of the screen, and we had tracked it from the bottom right corner of the cart and got some data points. The initial position was 0.55 meters, and the initial velocity was negative 0.7239 meters per second. The initial velocity was determined by calculating the average velocity of the cart over the first 0.2 seconds. The formula used was average velocity is equivalent to the change in displacement divided by the change in time. The mass of the cart was 1 kilogram. Here we can see the computational model that was developed. Similarly, it has an initial position of 0.550 meters and an initial velocity of negative 0.7239 meters per second. However, it is important to note that the net force was 0 as there was no change in velocity, meaning there was no acceleration, since net force equals mass times acceleration. And then, from our Newton's second law, we derived the velocity and position update formulas, and you can see this here at the bottom of the screen. Some of the physics principles used included Newton's second law, and from there, we were able to derive the velocity update and position update formula. Since F net divided by m delta t is equivalent to 0, we know that the final velocity is equivalent to the initial velocity since there was no net force. Similarly, the position update formula states that final position is equivalent to initial position plus average velocity multiplied by change in time. Comparing both models, we see that both had an initial position of positive 0.55 meters. However, the final position varied a little. The final position of the actual tracked time was negative 0.3 meters, while the predicted position was negative 0.348 meters, meaning that the predicted displacement was larger than the actual one. Over time, the slope of the actual position line decreases in magnitude, indicating a decrease in the magnitude of velocity, while the predicted line is decreasing in linear, indicating a constant velocity in the negative direction. Conclusions. As we can see, this lab involved Newton's first law and Newton's second law, in that since there was 0 net force, there was a constant velocity, and we were able to derive the position update formula and velocity update formula to create a computational model that models this occurrence. However, there were some slight differences, and thus we should talk about some sources of error. A possible source of error was the frictionless ramp. Had it been angled upward slightly, it might cause the speed of the car to decrease and the graph of position versus time to be nonlinear. This could account for why the actual displacement was slightly smaller than predicted. Additionally, the ramp was not 100% frictionless, meaning that there was an unbalanced force presence that caused the car to decelerate, also meaning the displacement would be smaller than predicted. What if the positive x and negative x axes were to change, the slope of the line would have been the same magnitude but opposite in sign. Therefore, instead of having a negative velocity, we would have seen a positive velocity of same magnitude. Similarly, the y-intercept or initial position would be negative 0.550 meters rather than positive 0.550 meters, and the final position would have the same magnitude but opposite sign. It is not possible to say exactly how many forces were added together to give a 0 net force in this case we observed. While the experiment was created in an environment where constant velocity was trying to be possible, the card eventually decelerated slightly and there was a marginal net force. Thank you so much for watching, and I hope you enjoyed.